Hello everyone. In one of our previous videos, we derived the equations of motion for an N-link robot using the Lagrangian formulation. And if you remember, the main advantage of the Lagrangian formulation is you can avoid the reaction forces at the pins and other locations. Those reaction forces, the net work done by them is zero. So they do not really contribute to the overall motion of the system. And the Lagrangian formulation does skip them because they do not show in the potential or kinetic energy or in the generalized forces. Now, sometimes it does really matter for us to calculate these reaction forces. Why? Let's say we are going to design a robot, and one of the important things is to know the reaction forces at the joints so we can design joints that will not fail under the dynamic load that exists in the robots, under fatigue and so on. So without us studying the load applied to the joints, we cannot really have a good joint design. And even if a robot has the best kinematics and kinematics analysis and everything, and the equations of motion are all well, the torques are good, everything, but if the joints fail during the motion of the robot, that is definitely not desired. So in those cases, the second formulation is going to be the Newton Euler formulation, and this is what you are familiar with from your dynamics, right? Sum of the forces is equal to time rate of change of linear momentum, which is mass times linear velocity, and sum of the moments or torques about the centroid is equal to time rate of change of angular momentum, where angular momentum is the inertia matrix I times angular velocity omega. So these are the two important rules that we have in Newton Euler formulation. And the important thing here is when you write these equations, you describe everything in which coordinate frame, right? Because you know for a robot, you have lots of different coordinate frames, right? Specifically for a link, you can describe everything either with respect to the body attached frame, which is a rotating frame, it has motion, it's not an inertial frame, or you can describe everything in the base frame, which is inertial, and with respect to time, the unit vectors of that base frame do not change, while the body attached frame, it has time varying unit vectors because they do have a rotation. So depending on which frame you write these equations in, you will get a different appearance of the final formulas, but at the end of the day, both of them will provide the same kind of motion and the same calculations for the reaction forces or torques or anything. So although they might look quite a bit different, but if you really do some heavy algebra and try to simplify, you can see that they are the same thing. Or if you do numerical solution, you'll see they give you the same number or numbers. So let's discuss each case. If we write everything in the base frame, okay? If we write everything in the base frame, what's going to happen? Let's look at the entities that are involved. We have the forces and the torques. We have the mass, linear velocity, inertia matrix, angular velocity. Which one of them do you need to care about? Which one of them is it that you have to pay attention to its variations? So, how can I write linear and angular velocities for each rigid body in the base frame? Well, that's not a big problem. We learn about Jacobians, and we learn that V and omega, right, can be written in terms of Jacobians, or you can directly use the kinematics formulas of rigid bodies, which is equivalent to that, correct? So if you remember from rigid bodies, you know that if I have a rigid body, then let me show you. So if I have a rigid body like this, let me try to draw it a little bit better. Here we go. If I have one point here, right, and then I have also the centroid here. If this one point on the rigid body, I might call it point A, and the centroid, I call it point C. If I know the velocity of point A, correct, so if I call this V of A, and the velocity of centroid is this one, V of C, I can relate V of C to V of A based on what we have learned in dynamics. And if you forgot about that, please watch my playlist called Dynamics and look at the velocity analysis of rigid bodies, okay? And you will see this formula and how it is derived. V of C will be V of A plus omega of the rigid body cross R of C with respect to A, where R of C with respect to A goes from A to C, this vector. Right? So this is what we learned from the rigid body kinematics. And similarly, also, if you remember, A of the centroid is equal to A of A. If I know the motion of A, both V and A of it, then plus what? Omega dot cross R of C with respect to A, and then plus omega cross R of C with respect to A, where this is called the relative centripetal acceleration and this is called the relative tangential. So this is called A of C with respect to A tangential, and this guy is called A of C with respect to A normal or centripetal. Correct? So these two formulas are what we remember from rigid bodies, and we can use these to find what? To find omegas, V's, A's, and alphas really that we need, or omega dots. So why don't we use the Jacobian here? We can if you want to, but since that Jacobian method we mostly use in the Lagrangian formula, here we are using the different analysis. As you remember, we used V and omegas, we determined them using JV and J omega. So again, we can do that, but we're trying to not mix the two formulations together, and here we're trying to stick to the knowledge that we had in dynamics in Newton Euler formulation, not Lagrangian dynamics. So why is this good? Because typically when you have a robot, then when you go to a link, you typically know the motion of one end of it, and then you're trying to find the motion of another end or the centroid. Let's say here, if it's if I know, let's say, the omega of the first link, omega 1, right? V of A can be considered as pinpoint because pinpoint has zero velocity. And if I know omega, then I can clearly find V of C1. And when I find V of C1, I can also find V of point B, the next joint. And when I have V of B, if I know omega 2, then again, I can find what? V of point C2, as well as this point, you might call it something else, maybe D. And once I have D and I know omega 3, I can find what? V of this C3 as well as the end effector. Correct? So that's what we are going to do in this formulation. Is called the recursion. And so we start basically our motion analysis from the base, because the base is stationary. We know it has the stationary point on the base has a v of 0 and a of 0. So we start from there and then go one by one all the way to the last link, and we calculate the velocities or the accelerations of all of the centroid. Especially the acceleration is what we care about, this one. Why? Because that is what you will see in this formula. Here we assume that for a robot the masses are constant, and when mass is constant, then this is going to be what? It is going to be mi derivative of vi, which is going to be ai. But a of which point on the rigid body? That's the acceleration of the centroid, a of ci, correct? Centroid number I. So you see, if I can find acceleration of centroid I multiplied by mass of link I, that's sum of the total forces applied to that link I. So definitely I need acceleration, and as I said, I will do it through this formula. Now, why do I need to do a velocity analysis also? Many times because not always you have omegas for each and every one of the links. So through velocity analysis, you try to find omegas really, and you need omegas definitely in your acceleration analysis. So we always do velocity analysis, then followed by acceleration analysis to give me A's, and masses are typically given. Then I can find the forces on the rigid body, including the pin forces. Now, what about the torque equation? Well, the torque equation, similar thing. So it depends on, as you can see, omega, which we could find through velocity analysis, and I. Now, here there is something that we need to say about I. So as I clearly mentioned for you here, if we want to write everything in terms of base, then the linear and the angular accelerations can be written along the inertial frame using rotation matrices. Okay, because when you find this acceleration, you have to make sure we are writing now everything along the base frame, about the axis of the base frame. So definitely, if this acceleration is somehow measured in a body attached frame, you multiply it by the rotation matrix of that link, take it to the base frame. If everything is already written in base frame, then you're good. But we always have the option of what? Multiplying any entity that is written in the body frame, multiplied by a rotation matrix, and take it to the base frame. Mass does not depend on which frame you're using, right? The inertia matrix does, because if you remember the inertia components of the inertia matrix, there is x, y, and z in them. So it definitely does. Now, how do I take this inertia matrix here to the base frame? So if I know the inertia matrix about a frame that is parallel to frame I but passing through the centroid, and I call it II. If I want to know what is that I rotation, the inertia matrix in the base frame, I need to pre and post multiply it by rotation of that link and the rotation of that link transpose. Okay, so let me clarify this, and we have talked about it in one of my previous videos. When I talked about rotation matrices, we call this guy similarity transform. And I talked exactly about this similarity transform. I talked about principal moments of inertia and so on. So let me show you those. So here is the robotics playlist on my channel, and this is this video called Rotation Matrices Part 2. And you see here I defined the similarity transform, which is exactly what you can see here, and then I used it later to talk about the moments of inertia. As I mentioned over there, these moments of inertia, like when you have Ixx, is the integral of y squared plus z squared dm. So depending on which x, y, or z frame that you use, these values of Ixx, Iyy, Izz, or the product terms, they will all change. Okay, so it does matter which frame you are using for the inertia matrix. Now, Here, the important thing is this II, this middle one here, again, that is the moment of inertia matrix for link I about which frame? About a frame parallel to frame number I attached to that link, but passing through the centroid. So if this is my link number I, and I have a frame I attached to it, right, like this, let's say. So let's say this is xi, this is yi, and this is zi. And this is link I. Then this I moment of inertia is calculated about a frame for which the axes are parallel to this x, y, and z. So the same x, the same y, and the same z parallel to the body attached frame, but the origin of that frame is at the centroid. So about this frame is what you calculate I. And now you use the pre and post multiplication by the rotation matrix of this link I with respect to 0. You use that, and then using the similarity transform, you calculate the moments of the moment of inertia matrix for that link, but in the base frame. Okay, so this is everything if you want to do it in base frame. On the other hand, many times it's easier to calculate many of these entities in the body attached frame. You might say, why? Well, the reason is this. If you paid attention here, for my omega and v, when I want to write them in the base frame, I have to use the rotation matrix for each link and then take them to the base frame, correct? So I have to basically take my omega and v to the base frame using rotation matrices, pre-multiply by rotation matrix. But when I'm writing everything in the body attached frame, guess what? I do not need to transfer v and omega because they are already in that frame. Okay, so I mentioned that for you, that one. That the acceleration terms and the inertia matrix do not need to be transformed. Instead, you might say, well, that's perfect. Nothing needs to be transformed. The mass never needs to be transformed. V, omega, A, nothing has to be transformed. That's right, but there is one caveat here. What is the caveat? The caveat is here when you take time derivative. This inertia matrix that you have, right, which is like, as you know, IXX, IYY, IZZ, and then the product terms, correct, IXY, IXZ, IYZ, and then the mirror image of that. This matrix, remember, when we are using body attached frame, this x, this y, and this z, they are not constant x, y, z like the base frame of the robot. They are different than this x and this y and z. This x naught, y naught, and z naught, they do not have time derivatives. They do not rotate. These guys do. So if I say, what is like this xi hat, or the I, for example, does this guy have a time derivative? The answer is absolutely. It is equal to omega I cross that xi hat. Because that vector is rotating with angular velocity omega I in the space. But here, if I say, how about this x naught? Does this have a time derivative? And the answer is no. It is a fixed vector, fixed magnitude, 1, and fixed direction. So for that reason, this entity here, this I omega, when you calculate the derivative of that, it does have two terms in it. One is this guy here, which comes from the fact that omega does change with respect to time. You can have alpha. And the other one is because this whole entity, which we call angular momentum or h, this h is on a frame that is rotating with omega. So time derivative of that h is going to be omega cross h. So instead of this, you can replace it with h, and remember h is I times omega. Okay, so that's another term that you have, and that is what you can see here. Now you might say, here I only have one term. How come here you have two terms? Well, because in here, this unit vector had a constant magnitude. The magnitude of it did not change, only the direction of it did. But in here, this vector I omega can both change magnitude and direction. The magnitude of it can change because the magnitude of omega can change with respect to time. The direction of it can change because the direction of components of I, or the frame XYZ of link I, can change. So this is due to change in magnitude. Magnitude of what? The whole vector, because omega changes, then I omega does change. And this one is due to change in direction. Okay, so here you have two terms. And then, based on what we learned about the skew symmetric matrices, one way to calculate A cross B, right, if you remember from our introduction to skew symmetric matrices, A cross B can be written as a skew symmetric of A times B. And that's exactly what you can see here. This one is written like that. So the body attached frame has advantages. Many of the things do not need to be transformed. But when you come to time derivative of the angular momentum, you have two terms. So we have to keep that in mind. So in general, there are two ways you can handle it. Write everything in base frame or write everything in body attached frame. Typically, the form of the body attached frame will be a lot easier and nicer than the base frame. And that is what you are going to see in these derivations and these formulas, equations 1 to 6, which we called forward and inverse recursion formulas. So here everything is written in the body attached frame basically. But I can show you also, if we use the inertial frame and write everything in the base or inertial frame, we can get another way to formulate this. The equations, as I said, might look a little bit scary looking compared to body attached frame, but that's another approach. So first, as I said, let's go and look at this general formulation for body attached frame. So here we use some notations and symbols. So here, this is what you can see for link number I. This is the schematic of link number I, and the centroid of link I here is shown. So this place here is the centroid. And these 2 points here and here are the two joints that link has, and it's connected to the member before that and after that. So this one connects it to link number I-1. This one connects it to link I plus 1, correct? So this is the joint with link I plus 1, and this is the joint with link I minus 1. And here we use two vectors, Ri, Ci, and Ri plus 1 and Ci, and these are the vectors from each one of these joints to the centroid of the link. Here, the only force, the body force that is applied to the link I is gravity, M-I-G-I. There are two reaction forces on the two ends, Fi and Fi plus 1. These forces are coming from what? From the adjacent links, link I minus 1 and I plus 1, and they are applying those forces through the joints to this link number I. Now you might say, why is it that you multiplied Fi plus 1 by a rotation matrix? Because here this Fi plus 1 is actually written in frame I plus 1. So it is actually like this, Fi plus 1, but written in frame I plus 1. So when I multiply it by what? By rotation of I plus 1 in I, it is like I'm bringing that force Fi plus 1, but write it in frame I. Because everything here has to be written in frame I. That's why you see Gi, Fi. Every force, anything, any torque has to be written about the axis of frame I. That's why I multiplied. And you might say, what is that negative doing? Well, that's action and reaction. This force is applied by this joint to link I plus 1 from link I, and then the reaction of that from link I plus 1 is applied to link I. So this negative is because of the reaction. The same thing goes for the torques. Here you have torque I, which is the torque applied at joint I by the motor. And then this torque I plus 1 is the torque that is applied to link I plus 1 through the motor, but the reaction of that is applied to what? Link I. And again, I use a rotation matrix to convert that torque that was already in frame I plus 1, bring it back to frame I, and negative again means reaction. So hopefully it is clear where each one of these 5 forces or torques coming from and why they are written the way they are written. Alpha and omega are definitely angular and angular velocity and acceleration of frame I. And A of Ci and A of Ei are what? A of Ci is definitely, of course, the acceleration of centroid of link I. A of Ei is the acceleration of end of link I plus 1. So basically acceleration of this point or this point. Right? Depending on what this I is. If it's I minus 1, it is going to be this. If it's I, it is going to be this one. So when I say A of E and I minus 1, that's this point. When I say A of E and I, that's the right point. It's one of the two ends. Good. So that's the notation. G is clear. F tau is clear. Rotation of I plus 1 with respect to I. That's the rotation of one link with respect to the adjacent link. In terms of Denavit-Hartenberg notation, this Ri plus 1 to Ri, we showed it with matrix Ai. Okay, that's the same notation. Mass is clear, I is clear, and again, pay attention, I is the inertia matrix of link I about a frame parallel to frame I, but origin at the centroid. So it's exactly this guy that I mentioned for you here, right? This one. And now going back, these vectors are also clear, right? There is r of I ci, r of I plus 1 ci, both of them you can see here, and then r of I plus 1, which we never use, but that's the vector directly going from one joint to the next. So this is like r of I and I plus 1. So now let's look at the equations of motion. So if you look at the free body diagram of link I, there are three forces acting on it. The forces Fi and Fi plus 1 and then mg. And so some of these three forces have to be equal to the mass of the block times acceleration at the centroid here. So that's what you can see over here, right? There are these three forces. Also, if you take some of the moments or torques about the centroid, mg doesn't do anything because it does pass through the centroid. The two torques ti and ti plus 1 transform back to frame I, they definitely do something. You have to add them together. They are coupled. And then this force F and Fi and Fi plus 1, they do also create moments about the centroid. For them, we need to use this position vector, this one, right, and this one. We have to cross multiply those position vectors by the forces. And if you look at these vectors, they are the same as Ri, Ci, and Ri plus 1 and Ci, but with the negative sign. So if I want, let's say, the moment of Fi about centroid, it's going to be this vector, which is really negative of Ri and Ci. That's this position vector here. And then cross multiplied by Fi. And a similar thing for this one. And as you know, if you change the order of a cross product, the negative sign goes away. So you can also write it as Fi cross Ri and Ci. And that's what you see here down in the equations of motion. So if you see F cross R, not R cross F, is because of that negative sign and reversing the order. So you see, these are those two couples, the torques. The torques due to the forces, that is equal to rate of change of angular momentum. And as we learned, this rate of change has two terms that you can see down here. So equations 5 and 6 are the equations of motion for the rigid body. And clearly, if you look at these equations of motion, they need some entities in order to be able to calculate them. One of them is acceleration of link I at the centroid. The other thing is angular velocity and then angular acceleration of each link with respect to either base frame or the body attached frame, right? So I have three kinematics quantities, A, alpha, and omega, that I need to calculate in order to be able to use equations 5 and 6. And that's where we go to our kinematics knowledge and kinematics equations, the equations that I earlier mentioned for you. So here we say that omega of link I in base is equal to omega of the previous link in base plus the RPM of link I multiplied by the unit vector of that direction. Right, so this whole thing is the relative angular velocity between frame I and I minus 1. And we can apply that here toward our example, 2 degree of freedom planar arm, right? In this case, if I want omega of member 2 with respect to the ground or base, based on this formula, it is omega of member 1, the previous member with respect to the base, and then plus the relative velocity of these two, correct, which is omega of 2 with respect to 1. But since everything here is written in frame 0, I cannot really write omega of 2 with respect to 1 unless I really multiply it by a rotation matrix of 1 with respect to 0, so I bring the whole thing down to frame 0. So what I do is, I say, well, this link 2 is rotating with angular velocity q dot with respect to 1. So the magnitude of the rotation is q2 dot, and the direction of rotation is the axis of z-axis of frame 1. So it is going to be like this, right? And clearly here your z1 is out of the plane, the same as z0, that is also out of the plane, right? So this one is definitely omega 1 with respect to 0. The magnitude of it is q1 dot times z of 0, right? Then plus q2 dot times z of 1 in 0. And clearly, if I call this guy to be k, this one is also k. They are both out of the plane. So it is going to be like q1 dot plus q2 dot, both of it times k. And that's what we also know from our previous videos. Correct? Because q2 dot is measured with respect to link 1, so I have to add both of them together. Note that this q2 dot is not measured from the base. This is measured from frame 1. So I have to add it to RPM of frame 1 to get the absolute RPM of link 2 with respect to the base. Okay, and that's exactly what you saw up here. Now, as I said, the bad thing about it is in many applications, these guys here cannot be easily directly measured, right? In this case, we were lucky because the previous link was directly attached to the base. But if I had one more here, let's say I had one extra link here, and I wanted to do some similar thing, say omega of 3 with respect to 0 is omega of 2 with respect to 0 plus q3 dot times z of 2 in 0. Good. The thing is, this omega of 2 with respect to 0, I do not have it. No sensor can directly measure the RPM of link 2 with respect to the base, because link 2 is mounted on link 1. So I can never get omega of 2 in 0. I can get omega of 2 in 2, really, with respect to the body attached frame. So a better way, better approach to this is instead of writing here all of these omega terms in the base frame, I can write all of them in the body attached frame I. You see here, everything is in the base frame. But I can, instead of that, I can write everything in frame I instead. What's the good thing about it? The good thing is now I need what? I need omega of I minus 1 in I minus 1, not in 0. And this is the omega that your tachometer or any other RPM sensor can directly give you. You can read it off the sensor, right? As well as this one. This is also directly measured in with the tachometers. So these are directly measured by RPM sensors, like, as I said, Hall effect sensors or tachometers. While this one you cannot easily measure. So writing everything in frame I in the body attached frame can facilitate our calculations and match our calculations to the physical measurements, to be matched with physical measurements, not to something that you cannot measure. So that's what we do. Instead of using this equation on the left, we use the equation on the right for equation 1, that everything is basically projected back into frame I by the help of these two rotation matrices. Right? So you see this omega of frame I minus 1 is now multiplied by r of I minus 1 in I, so it takes it to frame I. And this whole thing here again, which is q dot of I with respect to 0 multiplied by r of 0 with respect to I, and that takes that whole thing again back to frame I. So by the help of these two rotation matrices, again, I make everything what? Entirely written in the body attached frame. So in order to update my omegas that I need in equation 6, I will use equation number 1 in this red box, right? And now we have to talk about how to update. So far this omega is taken care of by 1. How do we update alphas? That's where we look at equation 2, and then how do we find acceleration of the centroids? That we need in 5, and that's where we go to equation 3. So if you look at equation number 2, all we have done is taking time derivative of equation 1, and you clearly can see that the derivative of omega became alpha, and then this term here, the second term, it has one derivative because qi dot has magnitude change, so it becomes qi double dot. And the other thing is because this axis zi minus 1 with respect to 0 does change orientation. So because of that, right, because that axis does change orientation, so the time derivative of that we calculate by omega cross. And here this whole thing is acceleration of frame I written in frame 0, and this is what we are going to also use in equation number 6. Then we write our acceleration of the centroid equation, right? So acceleration of the centroid can be found for link I through the left node or the left joint, and then plus the omega cross I, right? So here we are using the velocity of this point here, and then add the omega term, and that will basically give us the velocity of the centroid, and then we can take time derivative from that to get acceleration. And this is what you can see, that the acceleration of the centroid is again acceleration of the left node, right, in that picture, plus the tangential term alpha cross I plus the normal or centripetal term. And instead of writing everything in the inertial frame, we can write everything in the body attached frame. So you see, instead of writing it in frame 0, I can write it in frame I, and for that I will use again a rotation matrix to do the projections, because this A of the left node can easily be measured in its own body attached frame. So if you basically multiply by rotation of I minus 1 to I, it will definitely take it to frame I for you, right? The same thing that you have here. And then for that reason also you need your omegas and omega dots to also all be written in frame I. So you can have the acceleration of the centroid calculated but in frame I, body attached frame, instead of the centroid, which makes it a lot easier to calculate, right? Because again, if I have a sensor, this term here, this angular acceleration, and this term, they are much easier to measure in body attached frame. There is no direct measure of them in the inertial frame. And now you might say, well, okay, fine, I have omega and alpha for this formula from these top relations, right? So if I wanted omega, I have it, because this omega here and here, that comes from this equation number 1. So I have that one covered. The R vectors are typically part of geometry. The omega dot, I can get it from this alpha relation. And the only thing remaining is what is the acceleration of the left node or any specific node that I know something about it. Where do I get it? You say, well, you get that from what? You get it from the previous link, correct? Because this node on the left is the intersection point between link I and then what? Link I minus 1, correct? So if I want, I can find the acceleration of this point through the previous point, and for the previous point, if I know the acceleration of this point, what I need is this vector that goes from, basically, it is going to be like r of I minus 1, right? It's this vector that we have not used so far, this guy. This r of I and I plus 1. In this case, it's going to be r of I minus 1 and I. If I have acceleration of this point here, the left node on the previous link, and I know this vector, which is part of geometry, and I know omega of the previous link and alpha of the previous link, correct? Then I should be able to calculate this point. Once I know that through the info about this guy here, then I can calculate the acceleration of the centroid. Correct? So you clearly see you have to go back, and that's what we do, is called the recursion formulas. So if you look at these equations 1, 2, 3, and 4, each link, its kinematic entities, omega, a's, and alphas, are related to the previous link, not directly to the base. And the result of that is recursions or recursive or update formulas. So all of these equations 1, 2, 3, 4, 5, 1, 2, 3, 4, they are all recursive equations, and the terminology that we use for it, in this case, we call it forward recursion. So we say through forward recursion and equations 1, 2, 3, 4, 5, I can find all omegas, all alphas, and all acceleration at the centroids. Why do we call it forward? Because if you consider this robot here, again, this example of 2 degree of freedom planar arm, we always know something about the base frame. We know at the base frame omega is 0. We know alpha is 0. We know the acceleration of this point here, this is also 0. And once I know that motion, now I move forward from the base of the robot toward what? Toward the end effector of the robot, or toward what? The centroids of the links. So because I move from frame 0 to frame n, this is called the forward recursion. Once I know frame 0, I can get frame 1. Once I know 1, I can get frame 2, and so on and so forth. Right? So that's what we call forward recursion, equations 1, 2, 3, 4, 5. What are the initial conditions that you need? As I said, omega of 0 is 0, alpha of 0 is 0, a of c 0 is 0, a of e at 0 is 0, okay? Because the base frame does not move. So you start with this, and we find all of a's, alphas, and omegas. Then once I have all a's, alphas, omegas, I go to equations 5 and 6. Now, if you look at equations 5 and 6, again, these equations are also recursive. Each frame is related to the previous frame. But what's the difference here? Once, as I said, I have these entities that I need, in order to find the f's and the tau's, I need to go from the end effector back to the base frame. Because again, if I go back to this example of this robot, it's at the end effector that I know anything about the forces or the torques. Right? So for example, if the end effector is free, it doesn't come into contact with anything, then I know at this frame here, f number n is equal to 0. And also tau number n is equal to 0. Because there is no couple or there is no force applied to the end effector. Once I know that, then I should come here and calculate fn minus 1 and tau n minus 1. By going through equations what? 5 and 6. Right? And once I know the previous frame, I keep going backwards and backwards and backwards. So my direction of calculation is from end effector back to the base. And that's why we call these equations 5 and 6 that are kinetic equations, we call them backward recursions. And that's what you can see here. So in general, solving for equations of motion and the reaction forces and torques, in a robot using the Newton Euler equations needs applying equations 1 to 6. 1 to 4 are called forward recursion, 5 and 6 are called backward recursion, and they give you enough equation to solve for any type of problem. Whether it's forward kinematic dynamics or inverse dynamics, you should be able to solve for anything here. Now, let's go ahead and look at the application of what we just discussed to the 2 degree of freedom planar arm and see if we can find the equation of motion as well as the reactions at the pins for this robot based on the method we just learned. So what we have here, we have 2 links, L1, L2. The centroids are at distances LC1 and LC2 from the left node. They are not necessarily equal to L1 or L2 over 2, so the bars are not necessarily uniform. The MGs are shown, the angles are shown, Q1 and Q2. The coordinate frames of Denavit-Hartenberg are shown, frame 0, frame 1, frame 2. So now we have to start with the forward recursion, finding omega A's and alphas, and then go to backward recursion and find F's and taus. So here, let's do the forward recursion. So we know that omega of 0 is 0. So from there, we can find omega of 1. Omega of 1, if we want to find it, of course, you can easily show that is Q1 dot times K. And alpha 1 is Q1 double dot times K. Omega 2 is Q1 dot plus Q2 dot times K. And alpha 2 is Q1 dot plus Q1 double dot plus Q2 double dot times K. And you might say, well, where did you get those? All we need is to apply that equation number 1, right? Which says omega I, or omega I in I, is equal to what? It is equal to the rotation of I minus 1 with respect to I times omega of I minus 1 measured in its own, and then plus what? You have rotation of 0 in I, unit vector z of I minus 1 in 0, and then here you have Q dot, correct? And what you need, this one should be I minus 1 in I minus 1, correct? Or I in I minus 1, actually. So this is your update equation. Now, is that going to give me both omega 1 and omega 2? Absolutely. So in this case, you know you have rotation matrices 1 and 2. What are they? Well, your rotation matrix 1 with respect to 0, or 0 with respect to 1, doesn't matter. You can do the transpose of it. So rotation of 1 with respect to 0 is what? It is cosine of Q1 negative sine of Q1 0 sine of Q1 cosine of Q1 0 0 0 1. And then similarly, you have rotation of 2 with respect to 1, which is very similar, but except this is going to be Q2. Right? So these are the R's that you need. Now, what is omega of 0 measured in 0? Well, of course, it's 0. So let's plug in I equal 1 into that equation. Let me bring it to this side. What's going to be the result? Well, you know, omega of 0 in 0, that's omega of base. Base doesn't rotate. So when I do that, then I will get omega of 1 in 1 is equal to R of 0 in 1 with respect to 1 of omega 0, and then plus R of 0, 1 z of 0, 0, and then q dot of 1, 0, right? So this is, of course, q1 dot. This is your k. This is 0. And r of 0 with respect to 1 is the same as 1 with respect to 0, just transpose of it. Right? So it is going to be basically this matrix, just a transpose of it, multiplied by k, which is 0, 0, 1, and then times q1 dot. And all I need to change for this guy is to transpose it. So this is going to be sign, this is going to be negative sign. And if I multiply, you clearly will see that the result is going to be what? So this is going to be 0, this is going to be 0, and the last one is just going to be q1 dot. Right? So you can also write it as q1 dot times k. And that's exactly what I have over here, q1 dot k. And then you can do the similar thing, apply omega 2, and then for omega 2, you will get the same thing. So here you say I equals 2, and then you have omega 2 in 2 is equal to r of 1 with respect to 2, omega 1, and then plus r of 0 in 2, and then z of 1 in 0, and then q dot of 2 in 1, right? So what do we get in here? So this is r of 2 with respect to 1 transpose of that, which we already had above. So this is going to be basically cosine of q2, sine of q2, 0, negative sine of q2, cosine of q2, 0, 0, 0, 1 is the transpose of that. Omega 1 was 0, 0, q1 dot. We had it already from the previous case, correct? And that's the recursion, right? For omega 2, I have to use omega 1. So here, this is the forward recursion going from one to the next. And r of 0 in 2, this one is equal to r of basically, this is 2, this is 1, this is 1, this is 0. So it's going to be the transpose of each and every one of those two. And or 2 with respect to 0 transpose. So it is going to basically be like cosine of q1 plus q2, sine of q1 plus q2, 0, negative sine of q1 plus q2, cosine of q1 plus q2, 0, 0, 0, 1, multiplied by z1 in 0. z1 in 0, in this case, it is equal to 0, 0, 1. And then q2 with respect to 1 dot, which is simply the magnitude of q2 dot, because q2 dot is the angular velocity that frame 2 has in frame 1, so that's also we define as q2 dot. Now, note that in general, in this case, it was easy for me to say that unit vector z1 is just 0, 0, 1. In general, how do I get these z's? Because this z, you see it in the formula for omega, right? You also see it in formula for alpha. The question is, how do I get these z's? And if you remember, we can get them from dh. So if I go back to the dh forward kinematics, for each frame, I have a T matrix, T of I in 0, which is like A1 times A2 all the way to AI. And if you remember, this is like R of I in 0, D of I in 0, then 0, 0, 0, 1. And then this R of I with respect to 0, it has 3 columns. The first one is X of I in respect to 0, the whole unit vector, Y of I in frame 0, and Z of I in frame 0. So I can definitely get it from the third column of the T matrices that I have in forward kinematics using the DH method. Okay, so definitely in order for you to be able to do any of these forward or backward recursions, you initially have to find the DH axis, the DH parameters, the A matrices, the T matrices, so you can get the R matrices that you need all the time. You see, lots of the times you need tons of these R matrices. So all of them can come from what? From your Denavit-Hartenberg. So you definitely always need to perform some forward kinematics and determine all of these A's and all of the T's. Good. If you forgot, please watch my previous videos on Denavit-Hartenberg forward kinematics. So now if I perform this, what's going to happen? This first one is definitely going to be again 0, 0, Q1 dot. And then plus what? If I multiply this whole thing, it is simply going to be 0, 0, Q2 dot. So I can write it as Q1 dot plus Q2 dot times K. And again, that's exactly what you can see over here. Okay, so clearly you see, if I write it properly, I can get it. And you might say, well, in this case, it's kind of obvious that omega 1 is Q1 dot K and omega 2 is Q1 dot plus Q2 dot K. That's right, because the robot is too simple. If the robot is really complicated, it's not so easy to do all of those computations visually. If everything is not planar, if you have a combination of revolute and prismatic joints all together, then none of these computations is as trivial. Okay, so you have to go through those recursions and get yourself all of the accurate calculations. Similarly, I can go with the alphas, right? Alpha 1 is kind of obvious that it is Q1 double dot times K, because if you just do this one, right? If I just apply this, let me just show you for one of the i's at least, right? So for this formula, if I apply I equal 1, what do I get? I get alpha of 1 is equal to what? R of 0 in 1, alpha of 0, and then plus R of 0, 1, Z of 0, 0, correct? And then Q1 double dot in 0, and then plus R of 0 in 1, Z of 0 in 0, and then Q1 dot in 0. So you know alpha of 0 is the angular acceleration of frame 0 or base. So this is 0, so this is gone. What is this guy going to be? This is R of 0 in 1, Z 0 in 0, which is simply 0, 0, 1. And we just multiplied. You know, when you multiply that rotation matrix, write it. You multiply this by 0, 0, 1, Q1 double dot, or you can just combine them into something like this. The result of that, this is 1. The result of that is simply 0, 0, Q1 double dot. So basically this rotation matrix has no effect on it. And what about this one? Well, we just forgot one thing, and we forgot this omega to be added here. So this is going to be like, let me get this shifted a little bit this way. So this is going to be plus omega of 1 in 1 cross that. So what's happening here? Omega of 1 in 1 is going to be like 0, 0, q1 dots. This thing here also, when you do it, it is going to be like 0, 0, q1 dots. And when you cross product a vector by itself, the result is also 0. So that is 0. This initial one is 0. The only thing that is remaining is 0, 0, q1 double dot, which is the middle term, this one. Or you can write it as q1 double dot times k. And that's exactly what we have over here. Okay, and then you apply I of 2, you get this one, and you can keep repeating. So definitely using equations 1 and 2, I can get my omegas and alphas. Okay, so here I have done some cleaning, so I can write on the rest of the pictures. So you also need some r vectors that are needed for acceleration terms, right? So you need, you can see here I have these two r's, right? R of I, Ci, and R of I and I plus 1. Once you have those, then you can calculate acceleration terms from 3 and 4. So these are those vectors here. You have R of 1 in C1, that's what you need, R of 2 in C1, and then R of 1 and 2. And those are these vectors. This is the first one, R of C1 with respect to joint 1, right? Because that's joint 1, joint 2, and joint 3. The next one is this one, R of C of 1 in 2. And then the other one is R of 1 in 2, which is basically this vector here. So clearly you see the R of 1 C1, the length of it is LC1, and the direction of it says I. Now we have to pay attention, this I that it says here, here, and here, all of them are I's of frame 1. They are all literally I of this axis, x1 hat. Okay, they are not I of the base frame. Okay, and R of this C1 in 2, the length of it is clearly this length, which is L1 minus LC1, and the direction of this vector is backwards, so that's why you have this negative term. And R of 1 with respect to 2, the whole length is L1 and it is along I. Similarly, you can define R of C2 in 2, R of C2 with respect to 3, and then R of 3 with respect to 2, these guys, which you can see. So you need these vectors as well. What's good about using body attached frame? This is one of the places. Right, you see the expressions are actually all written with respect to local unit vectors, and these local unit vectors make life a lot easier than to write everything about this I and this j. Then definitely those vectors, you need a bunch of sine and cosines of q1 and then q1 plus q2 to decompose them along the global unit vectors, right? So when I use local unit vectors, writing it is a lot easier. Just we have to pay attention when we say I. What do we mean by I? This second row, all of the I's are referring to what? To basically this one, unit vector of x2. So please be careful about that. Now here we start with the forward recursion, which is basically finding the A's, and for that we start with the first link, then we go to second link. That's why we call it forward. We start with the base, go to first link, and then second link. So what we really do here is we start at the base. At the base, the acceleration of this pinpoint 1 is 0. Then once I have that, acceleration of the centroid, this point, is not going to be so hard because they both belong to the same rigid body. So I am going to use this formula number 4 for I of 1, and that will give me what? If I apply every term based on what we had in it, it will give me negative LC1 Q1 dot squared, LC1 Q1 double dot, and then 0. And does that make sense? Absolutely. Because if you consider those terms, the negative LC1 Q1 dot squared is about I, and I means local I or x1. So it is basically in this direction, negative. The magnitude of it is LC1 Q1 dot squared. And the other term is positive J, and that's LC1 Q1 double dot. So it looks like this. So LC1 Q1 double dot is the tangential acceleration, and LC1 Q1 dot squared is the centripetal or normal acceleration. So definitely, you see, it absolutely makes sense as long as you know what is I, what is J. You also need acceleration of this point here, and that you find it very similar to the same way that you found acceleration of C1, except instead of LC1, use the whole L1. So you see these two are very similar except for LC1 replaced with L1. One other thing you need is G. You see here it says G1. It's not G, it's G1. So you see, if you look at our equations, we are talking about GI. And what does GI means? It means to project the mg or g along the local axis. Okay, so that's this term here. It is important. So we need to really project this gravity force m1g1 along the axis of frame 1. That is extremely crucial here. Here is that force m1g, and then these are the axes along which you need to project. So this is my force. These are the axes, x, axis y. And this angle is definitely Q1, or this angle you might say. And so definitely the components are going to be m1g cosine of Q1 and m1g sine of Q1, and they're both negative, so that's why you see these components and there is no z component. So that's A of C1, which we definitely need in equation 5, and then once I have member 1 all figured out kinematically, which is called forward recursion link 1, now you go to link 2, because now you have acceleration of this point, which is provided here. Once you have that, now through link 2 you can find the acceleration of the centroid 2, correct? And that's what you can see here. Okay, do I need to find the acceleration of this endpoint? No, you don't need it, because that one is not attached to another link. So all you need is now AC2, and there you stop. Again, you have to project the mg, this time along x2 and y2. And for that, you need the total angle here, which is Q1 plus Q2. That's why you see sine and cosine of Q1 and Q2 with negative signs are used for projecting G. And when you get this AC2, again, each one of these two components are along the local x and y. Okay, so if each one of them are a component that you might call AC2x and AC2y, then the direction of them is like this direction and this direction. Okay, so now that your kinematics is done, recursion link 1 and 2 forward, now you go to backward recursion. Here you're going to use equations 5 and 6, but you start at the end effector first and go back to the base. Why? Because at the end effector, you can basically determine the forces. These are the forces that are applied by the environment. So if we assume no forces at the end effector, then F3, the force on really, if there was a frame 3, if there was a frame right after frame 2 on the end effector, the force on that is 0. And using that, you can find F number 2. How? So here you go to this equation here, this one. And in this equation, you plug in basically I equal 2, which gives you F2 minus R of 3 with respect to 2F3, and then plus M2G2 is equal to M2A of C and 2. F3 is 0. G of 2 is already calculated. AC2 is already calculated in recursions for forward recursion of link 2. So if you take this term to the left, right hand side, it becomes F2 is equal to M2 AC2 minus M2 G2, and that is again exactly what you can see over here. So this is the reaction force at pin number 2, which is basically this point here. So this is the force that member 1 applied to member 2, or member 2 applies back to member 1. But when you want to interpret that, remember, just like anything else, that F2, let's say if you find some magnitudes and some directions like 2i plus 3j, what does it mean? 2i plus 3j, what is I, what is j? Again, this is I, this is j, because you use I of 2. So if you found, again, let's say 2i plus 3j for that force F2, that means what? That means 2 units along this direction, and then 3 units along that direction. So your force is something like this. This is your F2, for example. Right? The unit vectors that you will find will be along x2 and y2. That's how you interpret it. When it says 2 and 3, it doesn't mean 2 along the base frame x and 3 along base frame y. No. It's 2 and 3. The direction of them are determined by x2 and y2, not x0 and y0. So that is the reaction force at pin number 2. And then you apply the moment torque equation, which is equation number 6. So here you're going to have 2t2 or tau2 and tau3. Then you have F2 and F3, right? Remember F3, if I plug in I of 2 again, right? So you have tau2 minus R of 3, 2, tau3, and then plus F2 cross R of 2 and C2, and then minus R of 3, 2, F3 cross R of 3 and C3 is equal to, and now you have I number 3 alpha, or I number 2 alpha 2, correct? Let me clean up in front of this area. And then plus omega 2 cross I 2 omega 2. And guess what? Alpha 2 and omega 2 are already calculated for me. So I have them. I2 is already calculated. And the good thing about this I2 is I do not need to use a similarity transform to transform it back to any frame, because it is already about frame I, or at least a frame parallel to frame I, but passing through the centroid. So I do not need to recalculate this I2. This is the part that you just use it as is. Omega 2 and alpha 2 already calculated. The R's are calculated. Tau 3 is 0. F3 is 0. F2 is already calculated in the previous step. That allows me to calculate what? Tau number 2, the torque that you have applied to this joint to rotate it, correct? So now you can calculate what? How much torque you need at that joint. So tau 2 and then F2. You found both of these now in this step using equations 5 and 6. So this is going to be your tau 2, quite long. And as I said, this is going to be your F2. So this one is equation of motion, because if I know the torque, I can find my double dot terms. On the other hand, if I know my double dot terms, I can calculate tau. This F2 is definitely what? Is the reaction force. For it, you clearly see I need G2 and AC2. And G2 is already here. And AC2 is what? It is also calculated up here. There are double dot terms in it. So this equation, if I want to determine the force F2, I also need to know the double dot terms. Okay? So this is also like equation of motion 2 because there is double dot in it. So I have to combine all of this together. If the Q's are given to me, if I exactly know Q1 of t and Q2 of t, if somebody has dictated these two to me and says, now find F's, find the taus, well, you can easily do that, because once you know the Q's, it means you can also determine what? The Q dots and the double dots. And once I know those, I can calculate any term inside these two last equations. And that means I can determine my pin force and I can determine my tau. On the other hand, if the taus are given to me, the torques at the joints, then I need to solve this equation along with another one that we derive for the next link. And in that, with tau 2 and tau 1 given, I need to solve for the double dot terms. That gives me differential equations, 2 second orders. If I can decouple them and solve separately for them, then through the numerical solution of that with the taus given, I can find Q1 and Q2 and the dots all numerically, and then I can plug them back into this equation, and that gives me the values of the force numerically. There is very small chance that you can solve these equations of motion with given torques analytically, because if you look at the equations, they are highly nonlinear. Highly nonlinear coupled second order ODEs. So once you know your forces and torques on link number 2, now you go backward to link number 1 and you apply I of 1 to the equation number 1. That gives you F1, the force at pin number 1. So it is going to be something like this, for example. And it also gives you the torque that you need at joint 1. And similar to tau 2 and F2, the components, when I say 2i plus 3j for F2 and tau 2, they were both about what? X2 and Y2. When I'm talking about tau 1 and F1, and I say like 4i plus 6j, here I and j means what? The axis of frame 1. Okay, so f1 and tau 1 are described in frame 1, tau 2 and f2 are described in frame 2 with respect to unit vectors of that. So be very careful. None of those are described in the base frame. So if I do that, now I have my f1, the pin reaction at pin 1. For that, I also need f2. So this f2 has to come down here. And then I can calculate tau 1. For tau 1, not only I need f1, right? I need a bunch of other terms. And if I do that and simplify for f1 based on what I have and do a bunch of simplifications, you will get tau 1 is equal to tau 2 and then plus all the other terms. And you might say, how come you have both tau 1 and tau 2 in here? Well, the reason is if tau 1 is applied to joint 1 here, and tau 2 is applied here, it's the relative measurement again. Because this tau 2 is relatively it's measured with respect to a frame that itself, it is driven by tau 1. So it is kind of normal that the real effective tau for the motion of that joint alone is kind of like tau 1 minus tau 2, which you can take this tau 2 to the other side. Okay, so here I have all of these equations, and that means I can now simulate the behavior of the system and find all of the reaction forces. So let me just put them all in some boxes for you: F2 tau 2, F1 tau 1. And for that, I also need to know G1 and G2, which and AC1 and AC2, and that's AC2, G2. And then here is AC1 and what? G1. So once I have all of this, then I am good to do any, let's say, MATLAB simulation or anything for that matter. So here, let me mark down what are these that you need to have handy here. Once you have these 6 equations inside these boxes, or more 8 really, you can simulate the total behavior of this simple 2D planar arm. So now imagine if your robot has 6 joints or something, how much more scary looking and much more complicated the shape of your dynamics equation is going to be. But as you clearly see here, the Newton method allows me to calculate f's that in the Lagrangian method, they disappear and they never show up. Okay, so here I'm going to show you a simulation of these 8 equations in these boxes in MATLAB. So here is the code. That is the script. You define all of your parameters. Here I made the LCs to be half of Ls, so the centroids are exactly at the center of each link. Calculate the moments of inertia. They are all defined global parameters. I have 2 torques, 5 and 3 Newton meters. I have these initial conditions, 45 and 30 degrees for Q1 and Q2. The omegas, we start from 0. We solve this set of equations for 2 seconds, and then here I have one function that I use with OD45 to give me the solution, Q1 and Q2 versus time, right? And that is this function. So here what I did, I solved for Q1 double dot and Q2 double dot from the governing equations, and then here and then I use those to be the time derivatives of q1 dot and q2 dot, because if you look here into your governing equation, this one here, right? If you look here, this equation is not only about q2 double dot, there is also q1 double dot in it. The same thing goes down to this bottom equation here. Also that one, right? Again, if you look at the last line, you clearly see in the last line you have both q1 double dot and q2 double dot. So what I did, I wrote the equations inside these two boxes, specifically for this last, for the bottom one is the last line really. So tau 1 equal the whole thing. I wrote those two as a linear set of equations, a coefficient matrix times the unknown vector q1 double dot and q2 double dot equals a right-hand side, right? So this is what I did. And A and right-hand side, as you clearly see, they are functions of tau 1, tau 2, and q's and q dots. And then I use inverse of A multiplied by right-hand side to get my double dots that I need for OD45. You know, OD45 only solves first order ODEs. Here you have two second order ODEs, so you need 4 dummy variables. And that's what you see over here. Please watch my video on solving dynamic problems, or what we call initial value problems using MATLAB with OD45. It is under my playlist MATLAB. And you can see how you can use OD45. So when I did that, then I have another function. I pass all of the q's, q dots, and the double dots. I pass all of them to those calculating functions. And those functions, based on these two formulas, will calculate for me f1 and f2, right? And clearly, when you calculate f2, you need to know your AC2, right? And you also need your G2. So these two guys here. And when you calculate your F1, you need AC1 and you need G1. So you need this one here and this one. So all of those are incorporated in the second function to give me F1 and F2. And this is this function. So when in my script I solve for q's, then I pass all of the results to this function. It gives me f1 and f2 as big vectors. And then here I'm plotting versus time the norm of each one of these vectors for each time point. And this is the result. As you clearly can see, it has a ton of oscillations. Due to nature of the physics of the problem, all of the centripetal and Coriolis acceleration will cause all of these oscillations that you will see. And even for a small robot with like 0.5 kilogram first link, 200 gram second link, 20 centimeters first link, and 14 centimeters second link, and some relatively small torques, if you look here, the maximum value of my F1 can go all the way up to something like 7,300 newtons. And the same thing for what? For F2 also it goes above 4,000 newtons. Okay, so definitely the load is variable, so you definitely will see fatigue in those joints that are subjected to the forces F1 and F2. But even if you want to design based on static analysis, which is absolutely wrong, but if you want to do that, what force do you consider here on the joints? Definitely you need to use the maximum force that you can see here, right? So these are extremely important for your design purposes to know how much force is at each and every one of the joints. This you cannot do by a Lagrangian method. And one thing that might cross your mind is, well, if I go back here for F1 and F2, what I really need is acceleration of centroid 1 and centroid 2. Can I find them by Lagrangian? Well, Lagrangian gives you these two equations of motion in red, gives you something very, very similar to that with the exact result. Okay, now when these two equations will give you Q1 and Q2 when you use OD45, right? And OD45 gives you Q1 and Q2. So you can also you can have Q dots and Q double dots. Then you can go and calculate AC1 and AC2 based on these formulas. So if I want to get to these two equations in red, do I need to use Newton Euler? Absolutely. But alternative is to get to these two equations also using Lagrangian. So I can get to these two equations either with Newton Euler or Lagrangian. But the rest of the equations that are in blue, you definitely need Newton Euler formulation. Okay, so this is the overall. Let me write them for you. This is the overall process for solving such problems. I'm going to share these codes with you under the descriptions, and hopefully they help you simulate this system and understand it a little bit better.